Hello everyone and welcome to lesson 14 of the Save My STEM Physics channel. Today we are going to be moving on to waves for the first time on this channel. So we've just finished quantum and particle physics and now we're moving on to waves. So the first lesson that we are doing is sort of GCSE knowledge. We're going to be going over the difference between longitudinal, transverse waves and mechanical and electromagnetic waves. So we're just going to start off with mechanical and electromagnetic. So mechanical waves are waves that require a medium. So a medium is just sort of any sort of matter, I'd say. So whether it be seawater, in which water waves pass through, whether it be air, which sound waves pass through, or the ground that seismic waves pass through, those are all mechanical waves because they require that medium to pass through. Something like a sound wave cannot travel in space because it cannot cause particles to vibrate. Um, Therefore, it is a mechanical wave. An electromagnetic wave is kind of the opposite of that. An electromagnetic wave, I'm not going to bother to write that down because I think it's reasonably easy to infer, is an electromagnetic wave is a wave that doesn't require a medium. So something like light, which travels from the sun to our Earth through the vacuum of space, doesn't require any particles to vibrate and pass the wave along. In mechanical waves, the direction the wave moves is the direction of energy transfer. The same applies for electromagnetic waves, and mechanical waves can be longitudinal or transverse. But what actually is longitudinal and transverse? Longitudinal is a wave which oscillates parallel to the direction of energy transfer. So parallel. I'm going to leave some space so I can get a drawing. And then transverse, it oscillates perpendicular to the direction of energy transfer. So if the direction of energy transfer is across that way like that, our longitudinal wave is going to look like this. Something like that, where we'll see that there's parts that are closer together and parts that are further apart, and the wavelength is from two parts that are the same. So from compression, which is an area of high pressure, to another adjacent compression. So if I just label that for you, we have a compression and we have a rarefaction, which is rarefaction. Transverse waves look like this. If I just move the page up there, transverse waves look like that, and they still transfer energy along that way, but the particles oscillate up and down rather than side to side like they would in a transverse mechanical wave. Sorry, a longitudinal mechanical wave. The way I remember that a transverse wave looks like this is transverse has the letter S in it. This kind of looks like a sideways S, so that's how I remember that transverse waves look like this and longitudinal waves look like this. So if I was to display a transverse wave in terms of particles, let's just say those are air molecules, just whatever molecule in the air, they're going to vibrate up and down. All of them will vibrate up and down, as the energy propagates through the medium. If we represent this one with air molecules, if we represent a longitudinal wave, then they will oscillate side to side. And their starting position is called their equilibrium position, or rest position it's sometimes referred to as, but equilibrium position is the terminology that we should be using now. So anytime a wave passes through this point, or sorry, anytime a particle passes back through that point, or that point, or that point, or that point, where the particle originally was, it is at its equilibrium position, and the equilibrium position lies on that axis there. Um, so yeah, that I think that all sort of makes sense. If we want to represent particles being at equilibrium on a longitudinal wave, what we need to do is we need to make a graph of pressure and wait, do we want pressure? No, we want displacement, sorry. Displacement. Not going to be able to fit that on. That says displacement. Not really. But yeah. And that says distance from uh I would say distance along wave. So if we take this for one particle, then the displacement is going to rise, so it's going to move right from its equilibrium point. It's then going to start moving left until it hits its equilibrium point, which is this axis here. It's going to move left away from its equilibrium point, and then start moving right back to its equilibrium point, and then hit its equilibrium point again. So anytime it's on this axis, it's on the equilibrium. Anytime it's moving downwards, it's moving left, and anytime it's moving upwards, it's moving right. Hopefully that all makes sense for you. For a transverse wave, it's much simpler. If it's moving up, it's moving up. If it's moving down, it's moving down. On this sort of graph. And I believe that is all we have to go through. Oh yes, examples of mechanical and electromagnetic waves, sorry. So, mechanical, ones that you will be expected to know, are sound, seismic, and water. Electromagnetic is anything on the electromagnetic spectrum. So, visible light, radio waves. I'm not going to list all of them, but you'll get the gist. Radio waves, gamma, rays. You could have microwaves, infrared, ultraviolet. There's one I'm forgetting. X-ray. You could have any of those, and those are electromagnetic waves. They're on the electromagnetic spectrum, and they all travel at the speed of light in a vacuum. Then for longitudinal, you need to know that sound is longitudinal. So, sorry about that. The longitudinal waves are sound waves and seismic P waves. Sorry if there was a jump in the video there. I had a massive brain fart. And seismic P waves and transverse are seismic S waves and the electromagnetic spectrum, or just light. Uh, Hopefully that all makes sense. That is the lesson on mechanical waves. electromagnetic waves, longitudinal and transverse waves finished, and that is the first lesson of waves done. Thank you very much for watching. I'll see you in the next one.